Guittot. My goal is just to make an overview of the load tracking. So we have done a lot of change in the load tracking mechanism in the scheduler for the past couple of years, and level 6 last year. So the goal of this session is mainly to make a status of what's happened and what's the status currently in the load tracking mechanism. Also, what is still missing or what we still remain to do, and then what are the next steps, what are the next big changes that we would like to work on, or an open question that's anything else. So, what happened since the last OSPM? So we already discussed this load tracking mechanism during the previous OSPM. And since this one, so several features have been merged in the kernel which are linked to the load tracking. So the first one is a new propagation mechanism, which also includes, so there was a first iteration, which was mainly for utilization and the load, and there was another iteration that had been put about that, which is the load, the renewable load tracking mechanism and the propagation. So we also have some stuff around the deadline and the boundaries so that we can now have a good view of the deadline utilization, the deadline scheduling class utilization, and so because you already want to implement the invariance and the selection of the OPP. And we have also made some change for the block idle stuff, the fact that we had some utilization and some loads which were blocked when the CPU was idle, so we both stayed out regularly to not impact load balancing or OPP selection. One last thing that has been merged recently is utilized. This has been done by Patrick. So the goal is to estimate what will be the final utilization of the CFS instead of just following. So once the CPU is idle, so we are decaying its utilization, then utilization needs to ramp up sometimes too slowly for us to reach the final value. So this is used to just estimate what should be the final value of the utilization at this point. There were a few other things around that, but that's the main feature that have been related to load tracking. So this was the load tracking mechanism for the product 9. So I have just reused the slide that I made for the last OSPM, where we were seeing that the load tracking was not stable. There was no propagation at all. It was told the value all around. So there was some change that when in the tip where some propagation was there. So that was the first implementation of the load tracking mechanism. But we can see that the load and the utilization of the CPU was still blocked. And we can see also that the frequency was increasing and decreasing regularly. So there was a lot of change, in fact, which is quite sometimes difficult to predict what will be the load, the system load, if you have everything that is changing over the time. This is now the status of the load tracking in the tip. So this run for the next year. So the first thing is that you can see that now the frequency, we are reaching the final frequency just at the beginning of when the task wake up. So when the CPU go out of idle, we can directly predict what will be the next final frequency. We can also see that we have some transition which are quite nice when the task migrates from one CPU to another one. So both utilization and load are migrating correctly.
This is using utilized.
So this is not really used to link to utilized. The fact that we are reaching directly the final frequency is linked to utilized. And we can also see that the share between C group, in a C group, the share of the load is more accurate. So we can see there that the load will decrease because of here. In this use case, we have two tasks which are running in different CPU.
Vincent, can you mention the workload? Because I saw some task running so that people understand why the signals look like this.
So it's exactly like that. So we have one large task which is working up from time to time on one CPU, and then we have a periodic task that wake up and migrate from one CPU to another one. Just to trigger the migration stuff, the fact that we are sharing the load, and the fact that we can have the task that the CPU that become idle with a large utilization and idle for a long time. So everything, it's always the same build.
Is that like a
Yes, sir.
is that a simulated workload? Simulated workload?
Yes, I'm using LTR.
Okay.
Yeah, just LTR is quite convenient to just trigger some use cases. Sometimes I'm doing most of the development and the test. It's not really LTR, just doing exactly what. So yeah, we can see that the utilization and the load are decaying regularly, and this helps also to increase the load of the other parts in the same C group. So that can give you more running time compared to other tasks which are not in the same C group. I haven't shown the runnable part there, just because that would create a lot of that noise, the switch in the signal, but the runnable load also follow quite nicely the load and the fact that task is running or not.
Sorry,
Yeah.
you said the final frequency is reached immediately, so
Yeah.
this is the scheduled governor, I guess.
Yes.
But it's and the driver is ACPI CPU track or Intel state
No, for
passive.
this one it's an ARM64, so it's a
Right.
CPU track DT.
This is a big improvement. This is very good.
Yeah.
We need to get
Yeah, yes,
Final.
clearly. Yeah, I mean, when you look at between that, where you were seeing that the frequency was increasing slowly. you
that was
have to
exactly
wait
the
for-
problem.
Yeah. I agree. So this one, yes, it look really nicely now. I mean, we can easily identify the different state in the load tracking. A question on that? So what still remains? So the first point that is remaining is the fact that the CFS, which has the lowest priority, can be preempted quite easily by RT and deadline. So other scheduling class can steal sometimes the CFS, and this can generate some frequency drop in some use case. Come back on that. And then the other point is that we have focused a lot on the belt for the CFS, but what about the system and the CPU utilization? In fact, we can see that in some situations we have a good knowledge of the deadline, the RT maybe not yet, and the CFS, but not of the whole system utilization. So how we can improve that?
Well,
And
what do you mean whole system, like GPU?
No. All the CPU from one CPU, how we are aggregating deadline utilization or deadline load, CFS load, RT load, to get something a CPU just of CPU. If you want one metric, if the CPU is used or not or not. Not really. We have seen some kind of regression from time to time. It's not clear what we really want to optimize. We have some metric, and I'm not sure that we are using that in the best way for now. And the last part is the scale invariance, which can create some. We have some invariance mechanism in the control tracking right now, but we still have some limitation with that. So yeah.
Yeah, so you had patches for that, like a year and a half ago.
Yeah.
Did you recently send them out? Because I couldn't find.
No, I haven't seen that
Okay.
recently. I see. Yeah, that's something I like to discuss with how we are tracking that invariance. There are several ways to do that. I have some patch, but I'm not fully happy with that. There are some limitations as well. So that's why I would like to see exactly what we want to track it.
My question is that what about the x86 for the scale invariant? So we're not doing that right now.
What one?
Any scale invariants for?
Yeah, I have a patch somewhere.
Yeah. I was basically wondering if we should try to do that.
I should dig it up. I've been too busy.
Yeah.
I think I've sent the patch to a number of people, but
I think that we have done that patch used.
And this, you're based on some Intel-specific register to get that?
So Srinivas
Srinivas has it. It's
has
also
the
been-
most recent version of it, I think.
Yeah, but Srinivas wanted something, I'm not quite sure, but it worked with Vincent's patches a year and a half ago. The reason I've not merged it is simply because we've been too busy with other stuff. But yeah, what it does, it uses the APERF, AMPERF registers that basically allow you to read the effective frequency at any over a period, and I read those registers in the tick because reading them is expensive. So I read them every tick, and then the scheduler callback it gets the most recent value. There are some complications in that APERF AMPERF ratio is not normalized. It can be, and it typically is larger than 1 because of things like turbo. It is max P, I think, is where 1 is.
Yeah, so if you are in the turbo range, it will be greater as well.
Right, and this is bad for scale invariance because then with,
So this
so I
is
renormalized it either dynamically or I allowed the architectures to set the scale on initialization.
Actually, I think this is the changes to make for Srinivas. Like when you have to basically know the maximum single car turbo.
So that's what I did. But Srinivas said he wanted the non-normalized thing, but that doesn't work for low.
Oh yeah. So you have to figure out what the max turbo is and then normalize to this.
Yeah.
Right? Yeah.
So I have some code for that that pokes into various
But
registers.
the problem with that is that different platforms have different ways to figure out what the maximum is.
I know. So I have one for Atom, I have one for V4. And if all of them fail, we pull back to the runtime. So every time you hit over 1, it renormalizes, and then you'll just clip at 1 for a while.
Yeah.
But so it should more or less work.
Okay.
But that mechanism involves stall cycles too, right? So it's more accurate because the input stalls. I think so. Yes.
You have to know.
Just for 8.4 we have very similar counters. They're going to be much more later, but now the opportunity to Symmetry basically the same, also the same as ACPI and CPC, which has the same feedback counters. So they might get. We did do a little bit of trying it out, and one slight, more than correct me if I get this wrong, the one slight, at the first pass from the first Friday, one slight issue was that the effective frequency that the counter created, we try and time constraint scenarios, don't know, might cut in and do something, ends up being less than the frequency that the kernel actually asks for. And then you get this kind of feedback effect where the cost of utilization is basically normalized to the current frequency. And then you end up asking for less performance because utilization was lower. And you get a kind of negative feedback loop.
Yeah,
And so the initial result was some benchmarks were lower than when you couldn't use it.
yeah, so that is stuff that
Yeah.
So there is an interesting feedback loop when it comes to utilization and tracking what the available capacity is, because the lower the capacity, then you might incur some schedules elsewhere.
Yeah.
And things
So
like
this is one reason why I had it depend on Vincent's alternative load tracking, because I think changed some of that.
Yeah,
But it's
it
been more
introduces
than
other problems then.
yeah. So, but it's been more than a year since I've looked at it, and I can now talk greatly about speculative execution.
I think the people who that's agree not to talk about it.
Yeah, I know. But so many of these details are gone from memory. But yeah, this is something we need to.
Coming back to the turbo rows, you really want to normalize against the maximum turbo, then if you are running the system in an area where you can't reach your turbo mode, then you basically can't fully utilize it. And in places in particular where we try to figure out if the CPU is fully utilized or not, you might not be able to actually make it look like it's fully utilized.
So the other option is to just clip it at once.
That's what I would do.
However, I think max P is getting to be lower and lower.
Yeah.
Yeah,
So then we're basically always running at 1.
Yeah.
Not only that, it is complete.
So
Like firmware. Or yeah, or files. Yeah, there's the register, right?
you can set max P. So, but yes,
problem is dealing with all this performance that you might or might not have. I mean, it's really difficult to optimize
Yeah,
for it
so
because
you
firmware might
can
decide
look
it's
at
there or it's not.
that this way. So the turbo range getting wider than the non-turbo range.
Yeah.
And in that case, you should put one, and you just not you're not taking the other part of the account.
No, but you can't trust that you have it anyway.
So-
Why factor it in? It's
so
just-
what we can do, and I've only thought about this as a crazy idea, is to track the average value and normalize to that, and then clip for everything above that.
That probably makes more sense because then it would sort of dynamically adapt to whatever environment your system is in and the use case you're running.
Yeah,
But there is so many feedback. But yeah, it's stuff we need to look at and try. But it is really hard. If on one hand, we can't tell the system what to do, and on the other hand, it can only more or less tell us what it did.
Yeah.
So I don't know.
So, I mean, even one is not right because we have the extra loads that don't even reach the nominal frequency. There is
I know.
not a one, and so if the idea is something wrong, what about using TDP?
Do we have that number?
Yeah, we could get it, I think. So yeah, because the TDP is basically what tells you what, you know, what the boundary is. That's it, right? And that's what it can.
Well, yeah, you can configure it.
Yeah, you can configure it.
See what?
Yeah,
so,
so that might be a good thing.
So, yeah, so these are the three main things that still remain, and I'm going to on that. The first one is that the case, that's a simple case with LTF. I have used LTF as well. So it's just that I have an always running CSS task, and I'm waking up an empty task that will empty task. And you can see that what's happened is that once the empty tasks start to preempt the CFS1, you can see that the utilization is decreasing, just mainly because utilization is about the running time. So we have less running time, so we are decreasing, which makes sense. The other thing is that we have a lot of frequency switch between, so the policy for the RT is going to max, the policy for CFS is just based on the utilization. But because the utilization is decreasing, we start to use lower frequency when CFS is running, whereas the CPU is always running. So we are creating this a bit change, but not really useful and even more. It's really bad for the performance. And another side effect is that because we are decreasing the OPP when the CFS is running, and the frequency is used for computing the load of the CPU is also decreasing, whereas we have an always runnable task on the CPU. So we have also this side effect that the CPU will see underloaded compared to another one, whereas it should be overloaded. I mean, fully used, fully loaded.
So if we do RT average with belt, then the capacity drop will more readily correspond to this drop. And then we can see that the average utilization matches the average capacity or the remaining capacity, and then we can see that it's still fully utilized.
Yeah.
But that would mean replacing RT average.
So that's
zero.
yeah. That's so the goal is to track. The proposal is to track the RT activity with something similar. So we are on the same time scale, so we can easily compensate. We need to sync the windows. In this, you can easily see that so we have the CFS utilization, which is increasing because the RT is increasing. So we have a better idea of the CPU utilization, and in CFS can prevent to go back to a lower frequency. The point between this kind of RT utilization compared to what RT average is doing now, that we are not in the same time scale. And also we have this proc interface for the RT average where you can specify. So it means that we will not be able to take this input into account in the RT average.
No, just
Okay. So that will be fine. But otherwise, yeah, that would be good to do something like that, to replace completely. So yeah, and in this case, we can see that we just stay at the max OPP.
Just one note, if the task is really preempted and never stops the CFS task with utilized, we should still see the estimated utilization to be fully utilized on the CPU.
Sorry, which one?
So the CFS task is always running task is always preempted, right? And if you predict the full utilization when the task is in queue, then you will always see the full utilization for CFS until it's the queue where we catch up.
You mean with utilized?
Yeah. So the bad signal will decrease, but the estimated utilization will still be 100% until the task is queued. And there was actually some discussion with the past intern about utilized where potentially when we queue we updated the estimated utilization, but if there has been preemption, probably we should skip the update because we cannot really see the task has been queued. We cannot really accumulate a value, so we should skip the update in that case.
I am not sure, but I think that I have used the latest skip team for this. So I think
is
there.
I never really tested this case,
so like that, I'm not sure, but I would say that we have utilized in this case.
So the utilization bandwidth goes down.
Yeah.
Like it's just the capacity, and when we have the scheduling, that we should not lower the frequency.
Yeah. Except that if we have some frequency switch, it probably mean that. Yeah, I don't know, to be honest, because I'm almost sure that I've used the latest. And this is
DQ, so your utilist also would.
No, that's for the activity task,
not for the clear task.
Utilist won't be because it is actually not running
CFS utilization now has to climb all the way back up. So you think you have 100% CFS task and tracking comes across, and CFS utilization down, then the RT task not anymore, but this task is always running, and it has to.
Yes, it will go back to.
It has to climb back up. So
Well, and I have used this case of an always running test that view speed can work with the test that is. I mean, we can have a use case where the CFS task is going back to idle from time to time.
Yeah, if it goes back to idle right now, we accumulate a sample and you
just this one I would say is the worst case because it's easier to highlight the problem.
Still, there is a little bit of we don't go straight down to the bad value because we go down with an average, so we should be a little bit compensated, but it's better.
So so there is a patch set for that to track points. So we are just tracking the RT root utilization, and we are adding that for the for in-scheduling. We are using that in scheduling. So which means that
you can give Jericho's question there. You can do the same for interrupt and the same for deadline.
That's the next step. Yes.
And then you can sum them all together to decrease capacity.
For deadline, you don't really need it, right?
No, but you can use the average deadline to decrease the CFS capacity. not use it for frequency stuff.
I mean, the average to be less. I mean, less conservative. I mean, in principle, you can use the admitted utilization for medley, but that's probably too
That's
pessimistic. Yeah.
best effort you can use the average.
Right. Yeah.
Yeah, that's the point. Because for now, in the so
One more thing. So as solution to the previous problem, there not any like other than the like maybe don't like the CFS, but don't like share.
that's normally right now the definition of utilization is the running time. Just because if two tasks are preempted counting themselves, just to have an idea of the utilization of the CPU. So another solution could be to change. Yes.
In this case, it's a different class. So
Yeah.
yeah, might be
And
different.
when a task migrate, that will be a bit more difficult. I mean, you don't have all the you don't have the CPU utilization, which is a sum of the task utilization. So that becomes more difficult to migrate tasks.
Well, on this topic, probably it has been already considered many times in the past, but have we ever reconsidered to factor utilization within the core scheduler? And so, well, we track also the real time, the deadline class. But yeah, so that's the point. And instead of having different signals and sum them up, we just track at the core scheduler, independent from the scheduling class, in that one single signal for everything.
Like what?
The running time.
Running time at the core scheduler level for all the classes. So it will give what you are proposing for FAIRE is just accounting also better.
Yeah, totally outside. This thing we have to better.
No, so we are not fixing that in CFS. The goal is to track RT. We are tracking CFS. It's in schedule till where you get the utilization of all everything and you decide. I mean, right now the proposal that I have made is to sum CFS and RT utilization when selecting the people for not RT task and the deadline. But we can decide whatever we want at the end. It's just that the main advantage is that you can split and you can make some decision in the governor.
So the reason we've not done that is part overhead and part the whole C groups. C groups for deadline don't exist. C groups for RT are a mess. And basically all we need here are the run queue averages for the other classes, not the task and group averages.
Implement that CPU level for two other classes, and then just let CFS be a special case where we actually track it.
Well, I guess I think your patch already put like the path in a different file, right? It's isolated the thing.
And I don't mind that, so I say don't just do it for RT, do it for deadline, and do it for the inflow, and make sure all the windows are aligned.
That at the IQ level.
So already, I think your patch already puts like the belt code up in
Yeah,
a different
right,
file, so you can use that from.
Try to move that outside so you reuse the.
In this, we always said that we don't want to have calls like function calls in the fast part. With this pelt.c stuff, we might introduce them. I'm not sure if this. You said there is no issue. You measured it.
So
but
the last time on the previous version, I have just compare the two images, and they were exactly the same. I haven't done that with the latest version, but I remember that for one point I raised the point.
Yeah, so this is just a question. I mean, if we are fine with function calls like the update stuff for the shared entities, the block shared entities, and the CFS run queues, they will be function calls then.
Yeah,
probably.
That's a good point. LTO will of course fix that, but I don't know what the current state of LTO on GCC is. Slang is absolute shit. But I did not say that. Yeah.
Otherwise, it's a nice idea. I mean, but
I guess if you measure that, if you compare the images and you see that's making no difference, means that the scheduler has the opportunity to actually turn function into an inline function,
Yeah,
but it's not taking the opportunity of it. So maybe it's
Yeah, so
making difference.
DCC is fairly aggressive at doing that. If there's a single call site, it will typically inline.
Well, there are multiple call sites. So that's the point.
Yeah, so last time I tried to profile the NQ path DFS that's a ginormous assembly function. So it's really tremendously large. That's when I wrote branch tracking support for annotate, because then it would highlight which bits of the assembly were actually used versus without it there. But inline very aggressive.
So yeah. So yeah, that's another one I discovered recently. So the fact that with a periodic task, you can have some frequencies. So the yellow line is the frequency, and we can see that the frequency is going up and down when the CPU become idle. And from a power point of view, at least for the platform, this platform, it's useless because when the CPU is idle, whatever the frequency, we are not functioning. In this case, I don't know for all the platforms, but in some case, we don't really care about doing such kind of change. So it's really about the system utilization and what should be the, and when we are taking this decision of changing the frequency, we must take into account more than just the current utilization on the CPU.
That's because you have a utilization update on transition to idle.
Oh, so this happened with the fact that because the utilization was blocked, we were when the CPU, when the number of CFS running tasks was more than the CPU, we consider that the utilization is new, so schedule say we don't need.
But this issue also, I was able to see the same thing, and I had a patch to fix that, but posted last year, but so far, I think it's basically the same thing, that there's no point in if it's about a board item, there's no point in calling CPU the scheduler to drop the frequency, because the cluster is going to go to idle, so you won't say anything.
Yeah,
You have to know what's taken,
yeah.
But even the cluster level actually, the cluster is not allocated.
There was some power improvement, even if just doing like a blanket, you just want to go to idle zone calls, you're able to see power improvement. Because there's a cost to transitioning for no reason. And then on the wake up again, you have to ramp the frequency back up, so it goes down and up. And we use the K-thread for. So our products have the patch point merged, but
if I understand correctly, probably it's a slightly different problem than what you are describing.
Yeah, in this
now.
one it's in the schedule till when HR running is new, we consider utilization to be new. But now, so this was because we had block load previously. Now, with the fact that we are decaying the utilization, we don't have to take care of that. So we can just keep the current utilization, take into account block utilization. Over time, this will decrease smoothly. So the goal is that the assumption is that yes, if you're going to be either really short, you don't really care about changing the frequency. But if you're going, you will go back and reuse probably the same frequency. If you're going idle for a long time, the C state that you will select will just fall down all the core domain, and being at higher or lower level doesn't impact the proper assumption.
One point to me that is not really clear is that well, before we was using the blocked load to ensure that we don't go down, and that was your fix for later time. And now we have a new feature that when the CFS is empty, we just go down. The problem is that it's still a kind of a policy that is should not be probably in scheduled and not in the scheduler. The scheduler is currently informing scheduled that there are no CFS tasks, and then why we should consider the blocked load there in the scheduler. So that's a big question mark. I don't know
that's the thing that which metric we should use is to find a CPU or system utilization. So right now we are using the number of running tasks. Should we really do that? It was used before because of the blocked problem. Should we still need that? What is the utilization at the IQ level? So there is RT, TFS, deadline, IRQ. So yeah, we should get a metric for each class in order to have the complete picture and not only looking at one. And then depending on what you want to do, when one type of task is running or not, we can decide to aggregate, use one, going to max. After that, it's just a matter of what is the best choice. But I think that we first need to define which kind of metric we need and we want. Yes, and the goal is really to have these two main problems about underestimate the utilization of the CPU or avoid some frequency transition where we know it's not needed or when we think it's not needed. So,
yeah. So what the useless frequency transition? I was doing with deadline, and it's because the government catered to like you have a situation where deadline task needs to update, then if like useless frequency transition is already committed and it's in flight, and that delays the whole.
So that's one thing, and the other one is really about should we change? So
the situation is you have a down frequency transition that has been committed, and the government case writer is working on that. And at some point in the future, it's going to do that, but it's still. And then the deadline task wakes up.
I guess the problem with that is that we're basically missing the deadline frequency transition completely. Since the thing is committed, basically.
What should happen is the frequency transition should stop somehow, and the down transition because.
Right, but yeah, I guess the biggest problem is that not only we go down, but we actually discard the deadline saying, okay, I want to transition now. So basically, the task can run for I don't know a tick or more, like in the down frequency. So that's the. Right. Yeah, we should do that.
But that's we still have a time window where it can't change.
No, can change. I mean, it's a physical thing, so you cannot do much. I mean, it's basically you're unlucky. What I'm saying is that we shouldn't forget at least the RT or deadline request.
Is it not possible just when the k-thread returns, just check that this actually the utilization on pair with so do a check post the commit of the and if that's not aligned, we just trigger another one and the work.
In the case with that line, why do we actually down the different output? So that's fine.
That should no, actually that shouldn't happen.
Where we basically never ever go under.
But the fact is that the fact is that we still so we basically driving the frequency is in a less pessimistic way. So we don't keep the thing always there, even if the task is sleeping for forever. So if you're unlucky that the task that was asking for a frequency release is basically is need, then there is a CFS task running that actually asks for dropping a frequency, and then the task actually wakes up, then you're getting this situation. So the problem is that you might want to always stay at the most conservative way, but then you're wasting probably energy.
For a periodic task. Maybe if a task is defined to be periodic and not aperiodic, you can keep always the frequency there.
In the case, it's basically what's happening because I guess it's not always, it's not basically going down. So that's That's what Morten is
I
saying.
saw that the deadline utilization was dated when it does wake up.
When it wakes up, but you can go to sleep and still we keep the frequency high because then there is this zero lag time where we actually release, let's say, the
zero
request.
lag time, you keep it.
Yes.
Okay. Oh, yeah, you're right.
And then I guess what Joy was saying is that if you're unlucky, that you're after the zero lag time, so there is no more the request from a task. Then the CFS task wakes up, and I mean a lower frequency is computed, but then the task, I mean the deadline task wakes up again. Then you might, I mean you have to wait. And I guess I mean that's basically physical thing, so you cannot do much about it. But what's wrong is that right now we are basically forgetting if the deadline asks the request while we are servicing the CFS request. So then there is this period of time where we're not basically servicing deadline or RT.
But if we check when we return, we still see that deadline as asking for an again utilization.
That might work.
And realign it. And I was saying before, I mean, right now there is not a semantic where you define a deadline task to say if it is really a periodic or if it's considered to be really periodic. Meaning periodic means that we know that it will wake up regularly. Because if we add these semantics, we can switch the policy and always keep the frequency if it's periodic, or otherwise we fall back to the method that we have now where you accept to go down and who cares. Because most of the issues that we have is really with periodic tasks, so we know we can just stick to that frequency.
True, I guess we might use the reclaim flag for that. So if the task is reclaim one, then we use the zero lag time. If not, it means that it's like a more strict one and do what you're saying. Maybe? No.
And deadline is period, the deadline equals period also.
Maybe, but you can still be non-periodic and have like deadline equal to period. So yeah.
So we already speaking about that. So we have invariance right now in the tracking, which is based on the runtime and which mainly weight the utilization when we are activating utilization mode. The implementation is really simple and straightforward, and it's really efficient in that way that it's mainly just we are weighting the value. So the main drawback is that it's capping the utilization at the load to the current capacity. That's exactly what we have there. I think it's just the same. So this is the utilization for a task, a periodic CFS task running at different frequency on my platform. So we can see that we are capped by the frequency U for each test. And this can have an impact in the sense that the load is also capped by this frequency. So we can have some load decrease in some case. Whereas, at least what I would like, I'm not sure it is for everybody, but the goal would be to have the same range of load and utilization. So for that, we are really invariant. And that's the same use case as before, and that's the prototype we were discussing. So that raised the point that the utilization can go over the current what we call CPU capacity. But the main advantage is that, for example, the fact that you're scaling, you're going above or below one, you don't care because you will activate it. The goal is to say that if you spend twice more time to do the job, at the end you should finally get the same utilization result. But you will need twice more time. Correct? 3 minutes left. Okay. Just, and another point, well, so I have a prototype for that. I still have some issue. I was running several use cases, and the point is that so the first point is that what do we really want to track for utility? Is it the running times or is it the load that have been done? I mean, right now we're using the time just because it's quite convenient. We have this clock which is there, and we are assuming that the time just reflect the load of the utilization, and then we are scaling that. But um, at the end, what do we really want to measure? The amount of work that has been done, and we want to be that invariant across architecture. And just it's mainly an open question. So is it really that? And the goal would be to try to track some work in this, instead of that in this case. So either by using the current behavior that we are making the assumption that 1 microsecond is this amount of work, and then 1 millisecond more work. But that can help us to extend further way to track work. I mean, on CPU, we have this ABF and there you can track how many instructions have been really executed on this piece.
I like that. The reason why, among other things, is because then you can have to do the cost, right? Which you can do with
Yes.
Micro-architectural difference in terms of instructions executed. But I mean, this requires to access counters that usually they are not. I mean, they are generic counters. They are there, but you cannot use in kernel space because some application wants to. They are not architecturally dedicated to the kernel.
Going forward, they are not
Okay.
and actually, I've talked about that. I'm here confusing. Then I'm not architect. It means that instead of actually background, you have to do any beyond that. You're right, if you wanted to use it now, you would have to tables. No, not overhead. It's actually quite sort of right. So Per wants to have the right to reinitialize the values to the standard whenever you do the traffic. I have big fights with them, and he's like, well, you could use these standards to actually run machine control, so it just traffic, which is the more correct these things. But so far, I've never won the battle with this one.
Another thing that I have seen is that right now we are trying to be invariant on timer-based or sleep-based activity. It's just that right now we are trying to be invariant for systems which are timer-based. So we have this amount of work to do every, let's say, 10 milliseconds, which is quite fine with some multimedia stuff when you have to display, to render a frame or with a video playback. But we have other use case where, in fact, our load is more based, let's say, on a sleep mechanism. So you have to do a work, and then you will sleep or wait this amount of time. And the more time you are using to do the work, doesn't shorter your sleep time. And in this case, with the current way we are tracking, so the utilization will decrease just because we are using more time to do the job.
And iOS is a good example of that.
Yeah, exactly. So should we also try to track this sleep-based mechanism to say we need to run that as fast as possible? Because the sleeping time is constant. It's not fixed. Wake-up time is just 1 millisecond once we are finished. That's another conclusion. But yeah, the current design, it's timer-based. And just one last thing, it's the cost of our load tracking. So we are doing more and more. We are more and more accurate. I have just done a quick experiment, so I have just cleared most of the functions which are doing the load tracking. So it's not working for just for the purpose of the test. And with the skip type, I have seen a bit more than 5% difference in the result.
Did you apply it to a single CPU?
No, I have checked that I was using 2 CPU in the same cache level. So, but yeah, I mean, it was just a quick and dirty, just to have an idea. But that starts to be quite significant. So should we also try to have a look at how we can optimize? Is it really a problem? I mean, it's a matter of benefits and cost.
Some people are always complaining that it's too expensive. Everything's too expensive.
I agree. That's
Should we look at? Yes. Is it possible? We'll see.
Yeah.
So,
Removing C groups makes everything faster. Seriously, if the C groups are big, I don't care. I mean, I don't use C groups, so I'm good. I mean, all I do is VI and build kernels.
Out of the, so I was curious, out of the 5%, like if you try to track within that, what is most, what the composition over here? Like, is it the divisions or?
I don't know. I just mainly make empty the update load, the range update load CFSRQ and load S. It was mainly just to remove that, just to have an idea. I haven't tried to profile exactly if it's where it's.
So, is there any component which is like a load updates versus utilization updates? Because there is a little bit of duplication of certain computation that when we run per batch, we don't really need to do for utilization. Just removing the utilization update, can it?
It was just to have a raw idea. Because if it was only 1%, the noise.
Yeah.
But yes, maybe we can have a difference between utilization and.
What I want to say is that that might be expensive, but it also make you save something because when you can obviously move the load information from one CPU to another, you have more accurate information so that you can immediately write the frequency to the level that you actually need. While with CPU utilization based mechanism, like I don't know, vStater, you don't know what happened before, and there is this large box with lots of CPU and few tasks, and they bounce all around the CPUs, and you have no way other than waiting that it ramps up.
No, yeah, I agree.
So this is a 5%, which from my point of view, it's quite a lot. I mean, 5% is in my worrying.
Yeah.
But there is also the other side where you save something, because when you migrate and you know how to write,
Yeah. I mean,
if schedule turns out viable.
it was abused on the first chart that now was much more stable, and we can easily predict where to place, where to put the task.
I didn't know about that development. I left schedule 2 months ago, so I didn't know.
But what would be the alternative? We should go back to instantaneous load?
No. It just I just wanted to raise that to see that it's not for free. I mean, and I think it worth the cost, but
we still have the CPU load array on the run queue, right? With with those different indexes and stuff. So which has to.
Yes, there's a comment there.
Yeah.
It's still there.
yeah,
Exactly.
Who is using that?
The load balancer.
Yeah, I think all architecture use at least some of the indexes.
Oh, yeah,
And then we claim that we
really-
do need it when we do target load and
maybe at the NUMA level.
but also
the deep
I think also
level.
we in ARM for die
Yeah.
level, I think we use index 2, which
Okay.
probably we don't know what it does, but
And so we tried replacing this with things like the instantaneous load and block load and other things. But we had a bunch of regressions done, but nobody had time to figure out why and how and all that. So it's still there. But yeah, this is something that would be good.
I think last time we said we could just disable the shed feature for one kernel release and then see, because I'm not sure if anybody is able to essentially come up with an explanation why we need it or why we don't need it. Like,
So the original thinking behind this is that the load balancer works on increasingly larger groups of CPUs, which is kept quality. And therefore, having an increasingly longer term view of behavior makes sense. If you're load balancing between only the SPT siblings, instantaneous load is good. If you're load balancing between NUMA nodes and you're taking instantaneous loads, you're causing everything. enormous amount of balancing, which hurts. So then throwing the um, window over which you look at load makes absolute sense in that regard. It's just a question of whether or not we can replace that with some of the load tracking we currently have, like instantaneous load versus spot load, and now also utilize, which we don't actually do for load, we just do utilization. So that's the thinking behind it. How much of it?
But like for runnable load, currently we do use pelt load, right? That's why you essentially introduced this
yes,
propagation down, because Tejun had some issues with it.
Yeah, Facebook, secret stuff, Facebook didn't work.
Yep.